Hello everybody and welcome to this GCSE Chemistry video about rates of reaction, where I'm going to walk through some exam questions about the topic. As I go through, what I'm going to do is talk out loud about the science behind the questions, and I'll annotate the questions with my thoughts, and those will appear in blue, and any actual answers that are going to be awarding marks are going to be in green, so you'll be able to see which bits are the thinking and which bits get you the credit on the test. Okay, so here is the first question. What I recommend you do during the video is pause the video when new questions come up and then listen to me as I go through each question on a mark-by-mark basis. So in the rates of reaction first question then, we're looking at sodium thiosulfate reacting with dilute hydrochloric acid. And what I'd like you to remember is that this is a named experiment, and it's the disappearing cross experiment. And in this reaction, what happens is you get a white tile with a cross on. And what happens is, during that reaction, something forms that makes a mixture that's inside a conical flask go cloudy. And so what happens is the cross appears to disappear. And that's because the cloudiness gets in the way and the cross is no longer visible. And so you can't see that cross anymore. It's as if it's disappeared. Now, the reason why it becomes cloudy is this sulfur. The sulfur, as you can see from its state symbol, is a solid. And so what you would need to write on your mark space is that sulfur is formed. And this sulfur, and we can tell this from the state symbol, will be a precipitate. So sulfur is formed as a precipitate. And a precipitate is an insoluble solid. And so we'll put that as an alternative answer, insoluble solid. Each one of those gets us our first mark. And then the next question is about planning an investigation. And in this investigation, we will be looking at how the concentration of the sodium thiosulfate affects the rate of reaction with dilute hydrochloric acid, as we've just seen. Now, this is a really common rates of reaction question. The only 6 markers you can get really are to do with planning an investigation. And when you're planning an investigation, the thing to keep in mind throughout any of the questions is you need to make sure that you have stated somewhere in the question or in your answer to the question what the independent variable is, what the dependent variable is, and what the control variables are. There's likely to be more than one control variables. And so we'll return back to that once we've started drafting our answer. So I've already discussed the kind of core concept of the experiment. So we need to start by saying what we would do. And so you would measure your sodium thiosulfate and put that into your conical flask. And I'll just draw an arrow pointing to my conical flask here. You can draw diagrams in a question like this, and that would support your answer. So measure the sodium thiosulfate and put it into a conical flask. And then you would also need to measure your hydrochloric acid. And it's always good when you're talking about a method if you can sort of show off and say using a measuring cylinder, because that is a really accurate way of getting a fixed volume of any particular liquid. So we've measured our sodium thiosulfate, we've measured our hydrochloric acid using a measuring cylinder, we've put the flask onto the cross. So put the flask onto a cross, and then the final thing that we need to do is add the acid to the flask, and then the crucial bit here is that we start the timer. And I've not drawn the timer, but in any rates experiment, you need to be timing something happening. What we've written so far is a description of the method for the experiment, but we need to get a little bit more explicit now about what we're measuring and keeping the same. So the dependent variable, which is our result that we measure, is the time taken for the cross to become no longer visible. and then our independent variable is to repeat this experiment with a new concentration of sodium thiosulfate. And so in any experiment, you're always changing something, and our clues from the question was we were asked to investigate how the concentration of sodium thiosulfate affects the rate of the reaction. And so the thing that we're changing is always the focus of the hypothesis, like that. And then the final thing to do with our investigation that we can say generally about any investigation is that we would need to repeat our experiment maybe 3 times for each concentration and calculate a mean for each concentration. And so these kind of approaches will serve you well for any rates of reaction experiment. And then last of all, control variables. It's really important that we talk about the things that you keep the same in an investigation. And so you don't need to mention every single last thing that there is, but since we're changing the concentration of sodium thiosulfate, it's very sensible to think that a concentration of the hydrochloric acid would be a control variable. So concentration of hydrochloric acid would very definitely be something that we need to keep the same each time. Similarly, the volume of hydrochloric acid would also need to be the same each time. And then last of all, along the same themes, the volume of sodium thiosulfate would need to be the same every single time. When you're sort of racking your brains about what the control variables are, think about what could you do that might make that rate of reaction change. So the temperature of the room where you're doing this experiment would be another very valid control variable. This next question is about a different experiment where hydrogen peroxide, which has got the formula H2O2, is reacted and produces water and oxygen. Now this happens normally, but very, very slowly. But with a catalyst such as manganese dioxide, it happens much faster. So the first question here is that we're identifying the gas produced in this reaction. So to find the gas, we need to look at the state symbols, and we've got the little G there next to the O2. And O2 is the formula for oxygen. And so what we're being asked to do here is explain how we would test for oxygen. And we don't need to write long sentences here. We just need to say what we would use to do this. And oxygen supports burning. And so what we need to say is that we would use a glowing splint. And this splint would relight. So we don't need to write very much at all here to get us our 2 marks. And then the next question goes into a description of a student investigating how particle size of this manganese dioxide catalyst affects the rate of reaction. And so what they're doing, which I'll draw a diagram just down at the bottom to track what they're doing, they're getting a conical flask and they're putting 25 cm cubed of the hydrogen peroxide in it, and then they are adding a spatula of manganese dioxide solid to the conical flask, and then they're collecting the gas. So they'll probably have a delivery tube in here connected up to some kind of gas syringe, which will have a plunger in and lines up the side for measuring the volume of gas, and this plunger will gradually move out as more and more gas gets produced. And it says that they're measuring it every minute for 10 minutes. And then the questions, though, are actually asking us why this experiment might not have given valid results and how we can make improvements to get more valid results. So the options that we've got are not silly, none of them are ridiculous and can be ruled out, but these are improvements to the method that this student is doing. So option 1, measure the increase in mass of the conical flask. So that is a method that can be used in some investigations. It's not appropriate here for 2 reasons. First of all, it's sort of a completely different method, so that wouldn't work. But the second reason why it's not appropriate here is that the mass would actually go down during this experiment. So that wouldn't work. Measure the volume of gas produced every 2 minutes. Well, actually, that would give us less accurate results because we would miss quite a few measurements for our experiment. So that wouldn't be appropriate. We'd get a lot of gas produced in that 2-minute period, and so our results would tell us less of a clear picture. Now, place the conical flask in a water bath at constant temperature. That is our first yes to that one. That would be a control variable that we would want to have for our experiment. So we'd put a big trough maybe of warm water, or just any temperature of water, just to keep that temperature fixed throughout the experiment. The next option that we've got is that we can use a different concentration of our hydrogen peroxide solution. You can see here we've got 0.3 moles per decimeter cubed, and then they're suggesting 0.05 as an alternative. That's going to give us a less concentrated solution and probably produce less gas, and certainly it wouldn't help our method give us a nice curve of volume of gas against time. So that's not ridiculous, but that wouldn't be helpful for our investigation. And then finally, use a mass of 1 gram of manganese dioxide each time. Absolutely be helpful. Effectively, what this question is doing, without really saying it, is keeping our control variables the same each time. This next question follows a different student, student B, who's using a method which is getting us valid results, and you can see that they have plotted their results on a table. Now, for rates experiments, the graphs pretty much always look like this. We've got time along the x-axis, for this is the beginning of the reaction, and time is passing, and they carried on their reaction and kept taking results for 10 minutes. And then on the y-axis, we've got the volume of gas in cubic centimetres that has been produced at each particular minute. You'll notice there are 2 curves for the graph, one which is a solid line for the coarse manganese dioxide lumps, and another which is a dashed line for the fine manganese dioxide powder. Now, the question is asking us for the mean rate of reaction in centimetres cubed per second between the 2nd and 4th minute for the coarse manganese dioxide lumps. So there's quite a lot going on in that question, and they've given us an extra fact that we need to report our final answer to 2 significant figures, which is worth writing down, I think, underneath the answer space, that reminder, 2 significant figures. So the mean rate of reaction can be found from our graph by taking the change in volume from the graph by the change in time. And so our job in this question is to find out what the volume was at the first point in time, which is 2 minutes, and then find out what the volume was 2 minutes later at the 4th minute. And so here's how we'll do that on our graph. We need to first of all find the times in question. There is 2 minutes, and here is 4 minutes. And so we need to use our ruler and track up to the line what the volume was. And the question was about coarse, remember. So coarse is the solid line. And so what we find is on the graph, that is at about 45 cubic centimetres. And that is because each of these little squares is worth 2, and we are 2.5 squares up. And then at the 4th minute, we track that up, and we've hit a solid line, and so that is 3 lines up, and so 3 lines above 50 gives us 56. And so what's happened is we've gone from 45 to 56, and so the volume change is 56 take away 45, which is a change of 11, and the time change is in minutes, it would be 2, but we've been asked to give our final answer in seconds, so 2 minutes have passed, but that is 120 seconds. And so what we have to do is, for our mean rate, we need to do 11 divided by 120. And once we've put that into our calculator, we've got an answer of 0.09167. And they've asked us to give our final answer into two significant figures, don't forget. So the significant figures begin when we hit our first non-zero value, which is the 9, which means we need to report these first two. But what we have to do before we get rid of our third and fourth significant figure is round up. So our final answer, that 6, turns the 1 that went before it into a 2. So our final answer is 0.092. This next question sticks with the same experiment, and what we're told in the experiment is somebody is repeating this experiment again, still with the coarse lumps of manganese dioxide, but this time what they're using is 0.2 moles per decimeter cubed of hydrogen peroxide instead of the 0.3, which was the original concentration, and that's the concentration that this graph is presented for. So what they've done is they've used a concentration that is lower. And so because the concentration is lower, we're using fewer moles of reactant. So the reactant moles that we're using are less. But we can do better than that. What we can see from our concentration is that it was 0.3 moles per cubic decimeter, but now the concentration is 0.2 moles per decimeter. And so what it is 2/3 of the original concentration. And what that means is we will make 2/3 of the moles of product. And so because our product was a gas, what we'll do is we'll make 2/3 the volume of gas that we would have expected before. And if we take a look at where this graph finished previously, it finished at this volume, which is 60 cubic centimetres of gas. Now, if we were to split that into thirds, 60 divides by 3 to make 20. And so since we've got 2/3 of the original concentration, we will make 2/3 of the volume of gas that we'd made previously. And so our experiment will finish at a lower height, 2/3 of the height of the original. So what we can say here is that the finishing height of our graph is directly proportional to the concentration of chemicals that we used. Now, the second aspect of this graph, and this is the case whenever we've got a 2-mark sketch graph, the second thing that they will be interested in is how quickly the gas was produced. Now, we've already said that the concentration is lower, and so you should know that if the concentration is lower, the rate of reaction will be lower as well. So our gradient, which is directly proportional to rate, must be a more gentle gradient than before. And so our 2 points to note are the gradient needs to be more gentle, and secondly, it needs to finish at 2/3 of the original height. The second part to this question, and this is the end of the question about this experiment, is focusing on when somebody's repeating this using fine powder instead of coarse lumps. And the question is, why is the rate of reaction different? We've got 2 marks here, and we're explaining why. And so the first mark is for saying that we've got a greater surface area. And because of that, the greater surface area means that there will be more frequent successful collisions. Now, you don't have to have used those exact words, but what you must have is some reference to amount of time. So you could have said more collisions per unit time, for instance. But what you can't do is just say chance of collisions. We need some word that is to do with time. So frequency means they happen more often, or you could say per unit time or per second or per minute or something like that. This final question is about a totally different experiment where a student is trying to find out how temperature affects the rate of reaction between magnesium carbonate and dilute hydrochloric acid. And in this experiment, what they're doing is they are warming their acid to a particular temperature, 30 degrees C in this case. Then they're adding magnesium carbonate powder to the conical flask. This time what they're doing is they're measuring the loss of mass in the flask every 20 seconds for 140 seconds, so just over 2 minutes. So what they would have is they would have their reaction mixture in a conical flask probably, and it would be fizzing. That's why we're losing mass, because what we produce is we produce carbon dioxide gas. And so they would have this on some kind of top pan balance, and it would be reading 20.00 grams at the beginning, and they would be tracking the decrease in mass over time. So in terms of explaining why this conical flask loses mass, all you would need to say is that a gas is produced. I want you to know that when carbonates react, it's carbon dioxide gas, but for this question, that's not vital. And this gas escapes, and that's the second mark. Then the question moves on to ask you to plot a graph. And so what's quite nice about this graph is that the axes have been drawn for you. And so this would be, the question has lost its number of marks. This would be a 3-mark question. You'd get 2 marks for plotting your points, and you'd get the 3rd mark for a sensible line of best fit. Just a quick word about scale. They've given us these axes, but we still need to understand the scale. Now, between each major grid line, we've got 5 squares, and our values change by 0.1, which means that each square themselves is worth 0.02. So we're effectively going up in 0.02 or 2s in terms of working out where we should put our points. The time axis is a little bit easier. We've got 5 small squares equals 25, so 1 square is equal to 5 seconds. So here we are with all of our points plotted. These points which were odd numbers were a little bit of a pain to plot because you had to be halfway between the 2 minor grid lines, so they were a little bit fiddly. But now all we've got to do is to plot our line of best fit, and the recommendation here is one smooth curve going through as many of your points as possible. And don't worry too much if you narrowly miss one. What we absolutely want to avoid is what they call feathering. So you definitely don't want a line that looks something like this. And so one smooth curve that is steepest at the beginning and getting more gentle as the curve progresses. Much like we had for the previous question, it looks like it's starting to level off, like so. This is the final part of the question, and this is showing the data for the student after they'd repeated their experiment at 50 degrees C. And what we've got for the graph is the exact same setup that we've just plotted. We've got loss of mass in grams on the y-axis and time in seconds along the x-axis. What we've been asked to do in the first question, you can see there's 4 marks, so there's obviously quite a lot going on, is we've been asked to determine the rate of reaction at 50 degrees C when the mass is 0.95 grams. That's really significant. And give our final answer to 2 significant figures, and so I'm going to remind us that we need 2 significant figures at the end. Now, to do this, what we have to do is we have to draw a tangent for our graph. And a tangent is where we've got a curve. I'll just sketch one on the side here. If that's a curve, what a tangent does is it follows the gradient of the curve at first, and then it continues in a straight line. So where the original blue curve began to curve, the tangent is a perfect straight line, and it carries on in the original direction that it was going. So that gradient is constant. It is a linear part of our graph. And so what we need to do for this question is we need to draw a tangent that hits the curve at 0.95 grams. And so let's start with that. So 0.95 grams is towards the top. Here is 0.9 and here is 1.0. So 0.95 is halfway between the two, which is here on the graph. And so our tangent, and I'm going to change to green because our tangent would get us a mark, it needs to follow the gradient of that line. And so here is the tangent that I've drawn. And as you can see, it does hit my graph at the 0.95 grams position as it was intended to do. But I've drawn a really big tangent that goes all the way to the y-axis and all the way to this major grid line here. And what that's going to do is make our next steps much easier, because what we need to do is we need to turn our tangent into a right-angled triangle. And so we need to work out the gradient of the tangent by turning it into a triangle. And as we can see here, we have got some coordinates. So this line would be, in terms of the y-axis, that would be 1.10 grams. And where it meets the y-axis at the other end, that would be 0.68 grams. And so, just like before in the previous question, when we're working out our mean rate of reaction, here we are going to do the exact same calculation. It is the change in mass. Previously, it was the change in volume. And that is 1.10 take away 0.68, which is 0.42 grams. And what we need to do is we need to work out how long that took. And the good news about carrying my tangent all the way along to the x-axis means that the time at the beginning of my tangent is 0. And if we just track all the way down to the bottom, we can see that this is at 125 seconds. So my change in time is a lovely, easy calculation. It's 125 take away 0, which is, of course, 125. And so then our rate at this specific point is 0.42 grams divided by 125 seconds, which is, here we go, this is the answer. And so when we round it to two significant figures, remember, we need to check whether we need to round up or round down, and this gives us our final answer of this. Now, just to be aware of, when you draw your tangent, you might draw yours a little bit more steeply than I've drawn mine, or it might be a bit more gentle, so there would always be a range of possible answers that would be totally fine in terms of getting all 4 of the marks. Speaking of all 4 of the marks, where are we actually getting our specific marks from? Suppose we're not going to get all the marks. So you'd get your first mark for a correctly drawn tangent. You'd get your second mark would be for correctly working out either the right-angled triangle or the kind of the coordinates at the both ends of our tangent. And then the third mark would be for working out our rate using the calculation shown here. And then the fourth mark would be for correctly rounding that rate to 2 significant figures. And then moving on to the final part of the question, we've been asked to state the effect that increasing the temperature of the solution has on the rate of reaction, and then explain this effect in terms of particles and collisions. So if you don't mention both of those, you can't possibly get all 4 of the marks. And it's a 4-mark question, so the stating the effect will be very, very quick. And you don't need to elaborate, you just need to say that the rate will increase as the temperature increases. And then the explanation must be taking 3 parts. So first of all, the particles, since they've got more kinetic energy, the particles will move faster. Since these particles are moving faster, there will then be more frequent, successful collisions because they're just knocking into each other far more frequently. And not only are they knocking into each other more frequently, each collision will also be more energetic, or you could say it will have more force as well. Either of those, absolutely fine. Okay, that's all for this question walkthrough. See you again soon. Goodbye.